Welcome everybody to this webinar. We're going to be talking about numerical issues. And before getting into that, well, Gurobi's been around for already 10 years. And the team on Gurobi has over 20 years experience in optimization problems and numerical issues for sure. And actually, we have built this experience helping our customers. All of them use Gurobi on a daily basis. And the kind of applications that they solve, it's really wide, from accounting to programming to you really name it. And it's from this experience that this webinar is drawing on. So let's go to the Gurobi guidelines for numerical issues, or you may say why things go wrong, and more importantly, how to avoid it. So what are numerical issues? That's probably a hard thing to say. We may say that actually people talk about numerical issues whenever they encounter unexpected results from the algorithms, or even they get inconsistent results for the same problem. And the source of these are numerous. However, the most common ones, I will say, are these four. These are or can be more easily handled. The first one is rounding, which I'm going to be talking about. And then there is the problem of the big gap between theoretical numbers and what the computers actually understand and represent those numbers. And coming from that gap, it's also a common thing for us to forget that these numbers have limits, and those limits impose to what we can ask for regarding on precision. And finally, we are going to be talking also about ill conditioning. So let's get first on trying to understand where these issues come from. The first and probably the easiest one is rounding coefficients. Probably this is best explained with an example. And this can really be very, very dangerous. So this is a very simple example. Assume that you give the solver these two constraints. And you may look at them and you say, well, you know what? This really look like the same constraint. And the numbers are, well, close to be really 1/3. That 0.333 could be interpreted as 1/3. However, we always will interpret the numbers that you gave the solver as the true numbers. And if you do that, and you do the linear algebra and do the substitution, what you will realize is essentially these two constraints are really implying that x is 1 and y is 0. And this comes from assuming that the numbers that you're feeding the solver are what you really want them to mean. So if instead of using this kind of approximate a third number, you had fed the full precision, let's say these two equations, a very different story will have arisen. So essentially, you will do the algebra, you do the substitutions, and then you end up with this expression down here, which is 2 times 10 to the minus 16 times x plus 1 plus the same coefficient. And this is really, really, really close to be 1. And actually, Gurobi will say, well, this is 1. And essentially, what it will do is that drop one of those two constraints and accept anything that satisfies these linear constraint as feasible solutions. Whereas if you round it, as I showed before, you will be telling the solver only to care for x equals 1 and y equals 0, which in most cases is not what you really wanted. So this is very easy to avoid. And one thing to look out for errors is whenever you're feeding the numbers into the model, be sure to use the full precision allowed by the solver, which is 16 digits. That's the standard precision. I'm going to get into that. And actually, probably a good question to ask yourself is, well, why 2 times 10 to the minus 16? What's so special about that number? Why does Gurobi just disregard those numbers? And that brings us to the next topic, that the real numbers are not really real, at least not in the computer, or not the way computers handle these numbers. So that's what I mean. And there is an easy check for that. So you can open up your Python interpreter and type that expression, and you will see that you will get a true. And you look at it and you say, no, that cannot be true, but that's what the computer is saying. Well, you may think this is coming from, this is really tiny numbers, so maybe it's not so wrong to assume that that expression is almost 1. But surely, if you use huge numbers, that shouldn't happen. But that's not true either. So if you do this other experiment, so now I have 10 to the 16 plus 1, I compare it to 10 to the 16, again, Python will say that's true. That's really strange. Those are not really small numbers. To make a long story short, this has nothing to do with Python, really. This will be true if you test it in Excel, in R, in C, in Java, whatever programming language that you use. If you use the standard provided floating point numbers underneath, these expressions will always hold true. And it gets worse, really. So given these limitations, I mean, these kind of comparisons, then not even the basic algebra rules that we learn in school are true anymore. So not even associativity, like here. So if I add 1 plus that tiny quantity, and then again that tiny quantity, that's not the same as first adding these two tiny quantities and then 1. This is not equal. So really, numbers stored in the computer using the standard hardware is not what we expected or what we learned to do with numbers in high school. And sure, there are ways around it. Just to mention some of them, GNU-MP is one way around it. There are other tools, but all these tools rely on software-based implementations or handling of the numbers, and those can be very slow. And I'm going to be talking a bit more about that. And actually, you can inspect where these limits come from. In Python, you can say import system and then print the floating information, and you will see there is this quantity down here, epsilon, that is 2 and all those ugly numbers times 10 to the minus 16. And what's that epsilon? That's the smallest number that you can add to 1 and still distinguish it from 1. Anything below that, 1, won't be able to register in the computer numbers that we use. And as I said, there is no way around this. And that's what I mean by real numbers not being real, at least not in the computer. So that really means that we have to be very careful on how we do arithmetics in the computer. Now, let me explain a bit more about this. So what does this mean? Most platforms provide a chip-based implementation of these floating point numbers, this kind of approximation of real numbers. And this hardware is really, really key to get good performance. I mean, this using the hardware-based floating point numbers, it's 10, 100, and sometimes even 1,000 times faster than using any of the standard extended precisions around there. So if you really care about performance, you should deal with these numbers and their limits. And that's what Gurobi does. We use in almost all the code these double precision 64-bit numbers. And this is not too bad, actually. I'm going to show you that although these numbers have limits, if used within reason, they do provide meaningful answers 99.999% of the time. There is also this last part, which is very key. Since these numbers don't really satisfy associativity, adding up is not really an exact operation, whenever you are testing if an inequality or an equation holds, you cannot really test for equality of the expressions. You have to take into account that there might be some rounding error going on. And what do we do to handle that? Well, that's tolerances and user scaling. And this is key to understand. So what will Gurobi do? Will always, as I said before when we were talking about these rounding issues, we will always trust the numbers that you give. So for example, if somehow in your model you write 1 plus 10 to the minus 7 times x less than or equal to 1 with x being binary, Presolve may detect this expression because it will be hidden and decide that, well, that implies that x must be 0, which is a correct implication from what the input that you gave the solver is. However, I have to make an emphasis that this may happen. And why it may happen and it doesn't happen all the time? Well, because during pre-solve or even by cutting planes, we have to limit how much time we invest in trying to detect this kind of stuff. So not all the time we will be performing an exhaustive search on all the implications hidden in the model. And that's why it may be converted into this. However, when you solve the model and you get a feasible solution, you have to check if that solution is feasible. But as I said before, you cannot really check for equality on the constraints. And you need to introduce the idea of tolerances. So whenever we have a feasible solution produced by an heuristic or by solving a linear system, there are at least three things that we have to check. One is deciding if a given solution is integer or not. And what we do is that we define this tolerance called the integer feasibility tolerance to decide whether a given quantity is integer enough. The same applies to primal feasibility. Whenever we have to check that an inequality or an equation actually is satisfied, we don't test for equality here. We always allow a little wiggle room to say. And again, whenever you are checking for a certificate of dual optimality, the same happens in the dual space. And that is called the optimality tolerances. And those are three different quantities that actually you can move a bit. So what does this mean? And this is very subtle. So let me try to be very careful with what I say. First, the tolerances that I was describing before, they are absolute quantities. They won't change depending on the input numbers that you give. So if you change the scale of a constraint or of a variable, the meaning in terms of these tolerances will change. And you have to be careful about that. I'm going to talk a bit more about it. It also means that you may have a feasible solution that satisfies the set tolerance that I said before, but even having a solution that violates just, let's say, by 10 to the minus 7 a constraint, pre-solve or even a cutting plane may decide at some intermediate step on the algorithm to cut it off and to mark that solution as infeasible. And why that can be troublesome? Well, because it means that at least for models where the numerics are challenging, the optimal value may change depending on the path that the algorithm takes. So essentially, what this means is that these tolerances, especially for problems where it's hard to get accurate solutions, imply that there is a gray zone. There is a gray zone of solutions that may be considered feasible in some situations, but in some other situations may be considered infeasible. Whereas whatever is strictly feasible will remain feasible always. And then outside that tolerance region, then things will be considered infeasible. So whenever the problem has a big gray area, that's the case where you're observing numerical issues with your model. So how bad is really this? Because I mean, up to now, this is sounding really, really bad. However, people use optimization very often, and it's not that common for them to get into issues. So how come? There must be something going on in here, and indeed there is. So first, the fault tolerance that we use in Gurobi is 10 to the minus 6 for primal and dual feasibility, and for integrality is 10 to the minus 5. And let's say that you define your model and your right-hand sides are in the order of 10 to the 4, 10 to the 3. It means that the gray zone, the area where you may have some solutions to be treated sometimes feasible and sometimes isn't feasible, is really tiny. It's just around 10 to the minus 9 or 1 in a billion. So that's really, really, really small. And for most problems, that's just insignificant. So that gray area doesn't play any role. And that's why I said that the scaling is key, because you are the one who choose how big is going to be the coefficients in your constraints, or how big are the ranges in your variables. Also, this means, since the tolerance, as I said before, are absolute and not relative. That if you have constraints with very small active ranges, the solver may consider them just to be an equation. And the changes that you're expecting to see, let's say if the solutions move in the range of 10 to the minus 9 and 10 to the minus 10, then that is just not being seen by the solver. So you should also try to avoid ranges for constraints that are just too small, unless they are really equations. Okay, so what about variables? Because this was talking about constraints. So the same really applies to variables. Ranges for variables shouldn't also be too big for the same reason, because the bounds are, again, primal constraints. Although we treat them differently, you should also be careful not to have wide range on primal variables. And also for integer variables. I mean, if you have an integer variable with really wide ranges, let's say 1,000,000, maybe you should reconsider treating them as integer. Maybe they are just continuous, especially if that's kind of the range where they move. I mean, just a unit change here in the order of the millions won't change much, but you will be paying the price of forcing the solver to work harder to find kind of an integer solution for those ranges. What about the objective functions? So again, the same applies, because remember, whenever you are looking at feasible solutions, you also have to check the duality conditions to really state that the given LP solve is optimal. So what I recommend is to gear your problem so that the optimal solution is in the range of either minus 10 to the 4 or 10 to the 4. Otherwise, what you're doing is really pushing the dual feasibility. So let's say if you're talking about billions of dollars, a good idea will be to change the units in your objective function to talk about thousands or maybe 10,000s of dollars instead of, I know, using either dollars or cents, which will make the objective function blow up and make everything really harder. Also, for the same reasons that you don't want to have constraints with very small ranges, you should also try to avoid objective functions that are really tiny. So if your problem does have a meaningful objective function, what I would recommend is to either make it strictly bigger than 1 or strictly smaller than minus 1. And the idea is to move away from 0, again, because then there is a better handling of the coefficients on the dual side. And the only exception for this is when your problem is really a feasibility problem, in which case all the coefficients in the objective can be 0, and that won't hurt performance at all, actually. And note, all this is not too hard to achieve. It's really just changing the scaling in your rows, it's essentially changing the units on how you measure the activities in your rows, and also in the columns, and also in the objective function. However, as I said before, Gurobi will not do this for you. It's up to the user really to define what's the right range for all these quantities. So, how do you get tight ranges for constraints and variables? Probably the first thing that you should try is to use other information not available in the model to impose tighter bounds either in constraints or in variables. So let's say, I don't know, I'm trying to plan providing a service of dispatch and delivery. And in principle, I could have any quantity of trucks. However, I know, because I know the business, that I'm only considering 3 possible locations to store the trucks, and those locations won't handle more than 100 trucks. So you can give that piece of information to the solver, and the solver will use that information to really prune both the search and make everything much faster. And if you think about it a little bit, if you don't give that information to the solver has to consider the possibility of going beyond, although you won't have any use for that solution if it's relevant. So the first thing and most important is try to get whatever extra information you have at hand to get tight bounds on your variables. After that, change units from tons to thousands of tons, let's say, or from dollars to thousands of dollars. All the time, try to choose the proper units so that the range of constraints and variables is not too large. Where too large, I mean, hopefully not beyond 10 to the 4. And finally, there is a common use case on where you can get very big and small coefficients in the objective function. And that's what people do when they are really trying to do hierarchical multi-objective optimization. They will blend all these different objectives with huge coefficients for the most important objectives and then with smaller coefficients for the less important objectives. So that will naturally lead to huge coefficients in the objective function. However, now Gurobi supports internally this multi-objective optimization where each objective now can have reasonable values, reasonable coefficients, and everything, believe me, will be much easier to solve. So let me try to stress why scaling is relevant. And what I'm going to do is an experiment, a quick experiment actually. So what I'm going to take is take a problem, and then I'm going to randomly rescale the columns of the problem so that the optimal value in theory doesn't change. So I'm going to change the objective and the coefficients here, and then decrease the bounds if they are finite, okay? And I'm going to do that within a range coefficient. And I'm going to run this script. You'll get this script so you can look at it later on. This is a common problem, and this means that I'm going to scale the columns with a factor up to of 1, but it could be smaller randomly. And then I let Gurobi optimize the resulting model. And what you see is right away you get this warning. I mean, the coefficients are too big. Actually, here you see 13 order of magnitude difference between the smallest and the largest coefficient. That's fairly large. But Gurobi goes on, work a bit, and he finds a solution in about 1,000 iterations, and the value is 4.49 E3, something like that. Okay, it wasn't too bad. What if I now scale the problem with a bigger coefficient, so up to 1,000? Well, you see now the matrix coefficient range, and it grew. Now it's 18 orders of magnitude. You see again the warning. And now we are still getting the same optimal value. However, and this is key, it took longer in numbers of iterations. And what if I push it even more? Well, I can push it now to, let's say, 1,000,000. I mean, scaling coefficients for up to 1,000,000. The matrix range is really crazy now. Gurobi will do his thing and still is able to get the optimal value. It took longer, but now you're getting this extra warning. What it's saying is saying that although he tried really hard to manage violations, when he unscaled or when he finished the process of doing the optimization, he couldn't find a solution with a small primal or dual violation. So in this case, it's really extreme. Still got the objective function right. It took longer in number of iterations, but couldn't find a nice solution with small violations. And it's no surprise. I mean, you are scaling for up to 1,000,000. What if I push it even further? Well, if I go all the way to 100 millions for rescaling columns, now the problems really break down. So Gurobi is not able to solve the model, declare it to be invisible. And this has to do that the fact that Gurobi will trust the numbers that you're giving. So in theory, if the numbers were pure, scaling columns shouldn't change anything. However, since numbers are storing this finite precision thing, when you rescale the problem, you're really changing the definition of it. And you are risking even getting unfeasible solutions. And also, please remember, I mean, as we were increasing the scaling range, essentially making the problem harder to solve, the first times Gurobi was able to solve the problem anyway, but the price that you pay for that is extra computing time. So again, rescaling your problem may actually result in a faster optimization. So What else can you do to handle these issues? So one thing that you can do is actually do a combination of row and column scaling to get better coefficients. So let me explain this with an example. So let's say that I have this problem. I have 10 to the minus 7x plus y and x 10 to the 3, z less than or equal to 10 to the 4. What I can do is replace x with 10 to the 4 x prime. And then I get this constraint on top. But later on, what I can also do, I can simplify this constraint. And instead of having 10 to the 4 x prime here and 10 to the 3z and 10 to the 4 here, I have this simpler expression. So by combining, I move from a world where I had 10 order of magnitudes of difference in the coefficient in the matrix to only 4, which is better. And not only that, since the precision and the tolerances is absolute, as I was saying before, actually solving the system with this constraint, with the scale it down constraint, is easier than solving the same problem, but with the scale up constraint. And why is that? It's because I will still be asking for a 10 to the minus 6 tolerance in this case. Whereas if I ask for a 10 to the minus 6 tolerance in this constraint, it will be in a sense easier for the solver to find such x prime and z. Don't lie to yourself. So a common guideline that we provide is the range of coefficients in the rows and columns should be small or not too big. So if you encounter this problem, it's not too hard to say, oh, well, I can hide that 6 orders of magnitude in just adding these equations. Now everything looks nice, isn't it? Now, instead of having 1 and 10 to the 6, I only have 1 and 10. However, you didn't really change the problem. Actually, the same kind of epsilon unfeasible solutions still persist in the model. And actually, Presolve will detect this and will get back into this original stuff. So you're not changing the problem by doing these tricks. What you could do instead of that is do this. So you can change y by y prime where they are related in this form. And now what you will get is essentially you push these 3 orders of magnitudes here in this coefficient and you increase now the range of the variable. But the side gain from this is that now if y prime is epsilon violated, what you will get in x is really a very small possible violation of only 10 to the minus 3, which is really better. So this is improving the numerical of the problem, whereas the previous substitution is not really helping. What about big M constraints? So in principle, if you rescale the meaning of your constraints, of your variables, there shouldn't be any big M's. Because the range of the variables will be within 10 to the 4, and then everything will work fine. However, if for some reason you cannot really get away from those big constants like here, and you cannot change that with by changing this scaling on the meaning of x, what you can do that will improve numerical accuracy is to define these constraints as SOS constraints or as a general implication constraints, which was introduced in Gurobi 7.5. However, although you will get more reliable solutions and actually this implication of y being 0 than x being 0 will be always satisfied, the price that you will be paying is that extra computing time. So it will fix the problem of numerical instabilities, but the price you will be paying is more computing time. So don't forget that. So in summary, kind of the quick takeaways. Variables shouldn't be in general in a range outside minus 10 to the 4 and 10 to the 4. Also the same applies for the constraints, the active range of the constraints, meaning where the solutions really move. And also the same apply for the good solutions. The good solutions shouldn't be too far away from that range either. Also, you should not expect or try to compare quantities that have two different absolute values. So, if you try to compare 10 to the minus 10 with 1, and those quantities were computed through linear algebra, you're really asking for trouble. Avoid those things. And actually, if you change this in your current models, you might get surprised because it may give you a boost in performance. And why is that? Well, because Gurobi will try really hard to, whenever we find numerical issues, to solve it by ourselves, either I don't know, by going even to extra precision, or by changing the algorithm internally, or by turning off some parts of the code that in general help to solve it quicker, and so on and so forth. So really, selecting the right ranges for everything may be really key to even improve the performance of your current model. So give it a try. So how do you check if your given model has numerical issues, which is an important question? How we go about that? So probably the first thing to do is try to separate whatever you're doing in your code from whatever the solver is doing. And an easy way to do that is to use this parameter, guro par dump equal 1. If you do that just before calling optimize, then optimize will generate two files. One is called gurobi.reu and the other is gurobi.prm. The first one is an anonymized version of your model, and the second one is the set of all the options, non-default values that you're using just when you enter the optimization call. And this is key because essentially those parameters will manage and affect which algorithms are used and how they are used. So to really be able to reproduce whatever you're seeing, you need these two files. So after getting those, what you can do is, let's say, try to read the model back in Python and inspect. So you can do that easily by printing the stats, and that will give you the matrix range, the objective coefficient range, and everything. And that will let you see if the ranges of these coefficients are within reason or not. Also, if everything looks fine there, you should read then into the model the parameters that you were using. And after reading those parameters, you can call optimize. And you definitely want to look at the output. And the Gurobi outputs are designed to provide as much information as possible. We will output in different situations many warning messages. The most common one is this warning that the matrix coefficients looks too bad, or the objective coefficients, or whatever. Also, if you see this warning marked with tolerance tightened to some given value, that's really signaling that Simplex is struggling to find stable solutions. And it's usually the indication that your model indeed is having numerical issues. For sure, if you see warning switching to quad precision, it means that Gurobi not only couldn't manage by changing the algorithm, but had to try on working on extended floating point precision. I talk a little bit about that later on. And of course, if you see numerical error or numerical trouble encounter, if you see restart crossover, that means that now the barrier crossover is having issues with your model, and suboptimal termination is the same. Warning variables drop from the basis is just another warning saying that the Simplex is struggling with your problem. Unscaled primal dual violation, all that comes again from working in your original model. It means that Gurobi is not able to satisfy the tolerances that you ask for this given problem. So all those are signals, strong signals that you should think about looking in detail to what's going on. Also, you should look into the quality of the solution. So you can always print what's the worst bound being violated, what's the worst constraint being violated, and what's the worst integrality condition being violated. So in this particular example, bounds are very okay, 10 to the minus 8, so that's fairly good. However, in this problem, we are seeing a constraint violation of 10 to the minus 4, and actually it's almost 10 to the minus 3. That's really bad. However, the integrality side looks fine. So these will be signaling that my solution is not really conforming, and that probably Gurobi is struggling to find a solution conforming to the tolerances. You can also inspect the condition number, and I'm talking about that in a little bit. Essentially, the condition number is also an indication especially if it's really big, that the solver may be encountering numerical issues in your model. Other symptoms. So whenever you see that I change some parameter and now my solution changes, the problem goes from infeasible to feasible, or the optimal objective value changes, all these are strong symptoms showing that your problem has numerical issues. Now, most of these problems are usually just numerical, meaning that they are not truly bugs in Gurobi. We have a few, but it's really rare. Most of the time, please believe me, comes from numerical problems within the model. One way to see if that's the case is, for example, trying to solve your model with tightening tolerances. So let's, instead of asking 10 to the minus 6, you may try 10 to the minus 8. If now the solver becomes stable for the solutions or with the answer, that's a strong indication that your problem is lacking in good scaling. And beware, although tightening tolerance may solve the problem in terms of stability, again, you will be paying by extra numerical computations. So you are paying the price on running time. Don't forget that. Now, if you already improve everything, the scales look nice, and you're still getting strange answers, well, don't hesitate and call us. I mean, that's what we are for. So that was about detecting or assessing if you have numerical issues. So what can you do once you see that you have numerical issues? And there are some parameters within Gurobi that help manage the numerical issues. But again, this will not solve them. It will just try to walk around them. And as I said many times now, you will be paying in running time. So let's go with this. Pre-solve. Pre-solve can sometimes introduce some issues. One way to look at it is you read your problem, you now load the pre-solved version, and you can print the stats of this pre-solved model. If that stat shows that now your coefficients are looking really strange, then maybe pre-solved is the culprit, which doesn't happen that often, but it may. If that's the case, you can try turning it off altogether with pre-solve equals 0. Or you can say, okay, aggregation shouldn't be used. Aggregation essentially what we'll do is, remember that bad example of don't lie to yourself, of hiding 10 to the 6 with 6 constraints? Well, aggregate will essentially rewind those stuff and will show implicit big coefficients back into the model. So if you disable it altogether, that won't show up in the constraint, but remember, you still have those big numbers whenever you're solving the LP anyway. So be careful. Or you can also disable the aggregation fill-in. Essentially, Gurobi will try to strengthen constraints, and sometimes while doing so, it may introduce kind of ugly coefficients. If that's the case, then you can try by disabling this piece and see if that helps performance. Also think about using the right algorithm. In general, barrier is the fastest in general, not always. However, unfortunately, barrier is also more sensible to numerical issues. So you should try either primal, dual simplex, and barrier by itself and see if that helps to get more robust solutions for your model. So it's always worth a try selecting the root node method. You can also try to make the algorithms less sensitive to numerical issues. The easiest way probably is to use the parameter called numeric focus. By default, it's set to -1, which means Gurobi will handle it internally and decide what to do. You can disable it altogether, setting it to 0, and you can increase it all the way to 1, 2, and 3. And what Gurobi will do, depending on these levels, is to be more conservative on the Markowitz tolerance, which is handling how the simplex pivots are selected. It will also select when to switch to quad precision. It will also limit Gomery passes, which in some cases, especially for numerically challenging problems, may introduce issues. It may reduce the number of cut passes that we do, and aggregation, and so on. So this is a common thing for people to try when they're encountering numerical issues, to change the numeric focus to either 1, 2, or even 3. You can also try to change the way Simplex do its pricing by selecting different norm adjust values. If barrier is having trouble, you may try to use bar homogeneous parameter. If also you can try a different strategy for the selecting the crossover basis. And you can also try to disable cuts altogether, because sometimes, again, for numerically challenging problems, they may introduce more numerical issues into your problem. Again, you have to remember, all this is not really a fix for the numerical issues. This is just a work around them. The real way to fix them is really going back into the model and trying to change how you pose it. So this is the last piece I have for this presentation, and it has to do with the condition number. So up to now, what I've said is either problems come from rounding input, I mean, not giving enough detail, or because essentially the limits of the computer numbers imply that not everything can be done in exact arithmetic. But not all the problems really come from that. Some problems really come from the geometry. And that has to do with the condition number, what I was showing before as kappa. So the usual definition is, while the condition number of an optimization problem is trying to capture the idea of how sensitive your optimization problem is, or the optimal solution of it is, to small changes in different parts of the input. A common thing that is used as a reference for this number, for linear system at least, is known as kappa of A, which is defined as the norm of the matrix times the norm of the inverse of the matrix. But I prefer really the geometry interpretation, which has to do with how rounded the feasible region is. And for bounded sets, this is really simple. Essentially, what you can try to imagine is, what's the ratio between the smallest ball containing the feasible solution and the largest ball contained in the feasible solution? So let me give you two examples. So you may think, okay, I can work in optimizing something like a circuit, so defined with many linear inequalities at the border. So in this situation, the geometry of the condition number will be the ratio between that slightly gray circle outside and the darker gray circle inside. And that will be fairly close to one. And what the condition number says is that, well, if that ratio is small, then small changes in the input data should produce small changes in the output solution. And indeed, that's the case. So I have a script here, you'll get it later on, that does exactly that. I define a circle with, I don't know, in this case, 1,000 inequalities to define the circle, and then I move a little bit here and there, some coefficients, and re-optimize and see how much the primal solution changes. And if I do that, I get this. So out of 500 iterations, changing small coefficients on the order of 10 to the minus 6 only change the primal solution about in the same order of magnitude, 1.7, 10 to the minus 6. So this really shows that small changes, as the geometry idea was, will result in small changes in the optimal solution, which makes sense. So these problems are easy to solve. But what if I try to optimize over a very thin triangle, like here? So imagine if I stretch this triangle more and more, the circle contained within it will get smaller and smaller, whereas the circle that contains it will grow more and more, and the ratio will get to be really bad. And what I can do is essentially define this optimization problem, tree constraint, solve it, and then see what happens if I change a little bit, a little tiny bit, the objective function. And if I do that right away, I mean, even changes in the objective functions in the order of 10 to the minus 6 translate themselves into changes in the primal solution of 16th order of magnitude. And this is not because the solver is getting the wrong answer. Actually, these three numbers are showing how big the primal, dual, and all the other bound violations are, which is essentially 0. So the solver is getting the right solution for this horrible problem. The problem is that if you change a tiny bit your objective function, you really may get very different solutions on the primal side. And this is not to do with numerical issues, it's really to do with the geometry, which again takes us back to scaling. So essentially, if you have a good scaling, a problem that looks more round or square, if you wish, then everything should behave much better. Whereas if you have very thin areas, you are exposing yourself to having very unstable solutions. So remember that. Okay, recap to end up. Essentially, instability, it's not always coming from the numbers, it also comes from the geometry. Gurobi will never second guess your input, will really trust it. And the best way to handle these numerical issues is most of the time, think hard and rescale everything and maybe even change the way you formulate the problem. Thank you for your attention, for your time.